Okay, welcome to part 2 of section 5.4. I want to continue by taking a look at how you can solve an equation in which you are going to get some imaginary roots. So I'd like to take a look at number 5. So number 5, the question does ask you to solve each equation. What you'll do to start the process is subtract 45 from both sides. Okay, so 5x plus 45 equals 0. So when you subtract 45 from both sides and then divide both sides by 5, you'll end up with the following equation: x equals 9. We know we cannot simply, just when we square both sides, of course, we can't simply leave our answer technically as a real number because, well, there isn't a real number answer here. So what we'll do is we'll continue. In the past, you would have said no real answer, but now we know that when we take the square root of a negative number, we can say, well, I, in this particular case, the square root of 9 on its own is in fact just 3. Now, there's one other nuance that we have to account for, and I'm going to actually do that right here, right now. I'm going to maybe move my equal sign over a bit such that my final answer with plus or minus readjusted ends up looking something like this. So plus or minus 3i. One of the things that we're going to continue with later will be maybe applying things like graphing to this type of quadratic equation and seeing that in fact, even though it doesn't cross the x-axis, we can assess how these two, what we call imaginary zeros, play a role in justifying that, well, it is in fact that particular quadratic equation and its solutions. Quadratic formula is applicable as well, something that you've learned in the past. I'm going to continue on to the next page. So operations with complex numbers. So as it turns out, there are several operations. We've taken a look at some of them already. So I won't read through every single nuance here, but a complex number, as we already discussed, has this form, this imaginary unit of I squared equals -1. There is an imaginary part and a real part that we have to take into account. So a plus bi will be how we kind of define that standard form of a complex number. A being the real and A being the real, B being the imaginary. In its entirety, bi will be, of course, the full imaginary portion of that. You can combine like terms with a plus bi. If you add a plus bi, for example, to c plus di, you simply add the real parts, which a plus c are in that context, and then b and d are separate, the imaginary parts, so b plus d. The I is then attached at the end. Similarly, you can subtract quote-unquote like terms or combine them. Let's move on to the multiplication of complex numbers, which I did do on a prior video. I did FOIL something where it was 2 plus I and 2 minus I, where we did end up with a final answer that ended up being a nice result. In this case, though, it's kind of giving you a general representation of FOILing. And then in that particular kind of mindset, I guess, you could multiply a plus bi times a minus bi, which I did refer to as conjugates, complex conjugates more specifically. And when this happens, you always get a real number, which is kind of an important result when we're identifying certain aspects of complex numbers. To divide by a complex number, first multiply the dividend and divisor by the complex conjugate. So this idea doesn't just apply to basic multiplication, but also when we do some division, which we will take a look at today as well. Example 1, simplify. 6 plus I plus 4 minus 5i. So 6 plus I plus 4 minus 5i, the real parts here are 6 and 4. So 6 plus 4. And then the imaginary parts, well, 1 and the minus 5i, which on its own can be subtracted out as such, 1 minus 5. So your final answer then ends up being 6 plus 4, of course, which is 10. And then 1 minus 5, of course, which is -4, such that your overall complex number in standard form, A plus bi form, where a is 10 and b is -4, looks just like this. You can actually type this into your graphing calculator like I showed you in the last video. So for the sake of time, though, I'd like you to check that maybe on your own later. Example 2 is a similar problem. You've got your real parts, so 8. Be careful, -6. So you'll see that down below. And then the imaginary parts, 3i minus a -2i, in other words, 3 plus 2, which of course ends up being just simply 5. So those two parts come together quite nicely. A minus 6, of course, is 2. 3 plus 2, of course, is 5. Your final complex number in standard form is 2 plus 5i, a being 2, b being 5. Number 3, or example 3, we're going to FOIL. The result isn't particularly great, like we saw in the prior page and video, but foiling is certainly the only way to do this. So 2 times -4 first, 2 times 2i, that's outside, inside -5i times -4, and then last, -5i times 2i. First, 2 times -4, that's -8. Outside 2 times 2i, that's positive 4i. Inside -5i times -4, that's positive 2i. And then the last, -5 times 2, which is -10, and of course I times I squared. I squared is nice, as we already know, yields -1. 24i is the result of adding these two like terms. -8 minus 10 times -1, or -8 plus 10, ends up being just simply 2. Therefore, final answer 2 plus 24i. Example 4. Simplify. 3 minus I all over 2 plus 3i. Now, because our denominator has a complex number in it, similar to when we did a square root problem back in prior sections and chapters, particularly in Algebra 1, when you rationalize the denominator, this is a similar process. We're going to multiply numerator and denominator by the conjugate, technically the complex conjugate. So if you recall the conjugate of the quantity, let's say 2 minus root 3, the complex conjugate of 2 minus root 3 would be 2 plus root 3. So in this case, 2 plus 3i is what we started with. Therefore, the complex conjugate, that would end up being 2 minus 3i. And again, if you recall from the last video when we did 2 plus I times 2 minus I, we actually bounce back to that to show you what I'm talking about again. We did that in problem number 4. 2 plus I times 2 minus I, nicely you had outside and inside cancel. So first and last ended up being your analysis of math, in which you just simply take 4 minus -1 to get 5. Every time you multiply complex conjugates, you're going to get a real number. And that's about to happen here as well. So if you take a look, and I'll actually start with the denominators. So 2 plus I times 2 minus 3i, that's first, which is 4. Outside, which is -6i, and inside, which is positive 6i, and those are going to cancel. So think about how this looks. First, outside, inside, and then last, 3i times -3i, which is -9i squared. Every single time you multiply conjugates, the outside and inside cancel. This ends up just being -1. So you'll simply see here, which they did as well here, but I'll rewrite it as such. So you've got 4 minus a -9, or technically 4 plus 9, which ends up being 13. I would prefer that they leave this as a minus sign, though, so you can kind of see how that math continues to play out. So technically 4 minus a -9, or minus 9, excuse me, times -1, or 4 plus 9, which ends up being 13, which is correct in the next step. Let's move on, though, as far as what the numerator. Well, the numerator hasn't been simplified. You are going to have to FOIL that as well, which does entail a little bit more analysis, and the result is not as nice. 3 times 2, that's outside. Excuse me, that's first. So 3 times 2, that's first. Outside, 3 times -3i. That would be, pardon, -9i. Inside would be -2i, and then the last would be -i times -3i, which is positive I squared. This then again turns into -1. this turns into, when we add those two as like terms, so to speak, negative 11i. 3 times negative 1 is negative 3, and you really are thinking of 6 minus 3, which ends up being 3. Okay, so I'm going to have to make a correction here on the answer key again. As you can unfortunately see here, we're going to end up with a different answer, it turns out. So this is still negative 1, as we saw, as I showed on the side there. Negative 9i minus 2i is still negative 11i, but like I said earlier, 6 minus 3, because 3 times negative 1 is negative 3. That'll end up being 3. Okay, so 3 minus 11i all over 13, and actually the answer does look good. So 3/13 minus 11/13 I. That's the standard form complex number. Let's simplify for example here. I think problems 1 through 6 are a matter of just combining like terms. So I think it'd be wise for us to take on maybe a fraction or two. And I am going to be foiling anyways in the process. I think number 10 is a great start. So the basic rule of thumb is you can't have an I in the denominator of a fraction, just like we saw with roots back in Algebra 1. So I'm going to multiply by the conjugate. Well, keep in mind, the conjugate of 3 plus I is 3 minus I. Saying it, I just didn't write it correctly. So there we go. I'll fix that up. So 3 minus I, 3 minus I. Okay. So as it turns out, when you FOIL the denominator, the great thing will be that when you FOIL, you'll end up with a nice answer. Knowing that outside and inside will always cancel. First is 9. Outside is negative 3i. Inside is positive 3i. And will always cancel. So you're just going to have to write last as negative what? I times I. So I squared. Know that, of course, that turns into negative 1. Before I simplify that, let's finish up, though, in the numerator. 5 times 3, which is 15. 5 times negative I, which is negative 5i. And we're going to still then have a little bit more to do with the following. So we'll have 15 minus 5i. And that's all over what? 9 minus negative 1, or 9 plus 1, which is 10. Put things all together, we can simplify with what? 15 over 10 minus 5 over 10i, which is actually still not quite done if we simplify by reducing 15 over 15 tenths, 15 over 10, 15 divided by 5, which of course is 3, and that denominator divided by 5 is 2. That then leads to 5 tenths, which is a half. So 3 halves minus 1 half I. Now to finish up, I want to kind of bounce to 5-4 past notes. So these are prior year notes. And I'm only doing this because this might be a nice way to kind of get you connected to notes that you can continue to look at if in fact I don't, let's say in future notes, I don't continue particularly with questions that I have in the past, or I just do a select number of problems. So let me click on that, 5-4 past. Now, a lot of you already know that this is accessible to you because I've been indicating that in other videos. But let's just take a look. So back apparently a year or so ago, when I did this in prior years, you can see I've done other questions. So I've done number 7. I've done 1 and 2, for example. And I've even written the examples up above in a similar way that kind of highlight the final answer. I'm going to scroll back to a prior page, page 24, and you can see how in example 3, I went through and I graphed x squared plus 5 equals 0. Just to kind of make a point here based upon what I've done and what I will ask you guys to do in the future here with graphs. You can in fact graph the function x squared plus 5 equals 0. Turns out the function has roots of plus or minus root 5i, which doesn't technically cross the x-axis, but that's okay. We'll be using this idea to help frame our understanding as to, well, let's say I give you the zeros or the roots to start with. You can work your way backwards to the parabola, which is quite effective in various ways. So that's just kind of a precursor for things to come. Please look on OneNote for the homework for the next day and possibly the following.